So then I say the word is yours, Arne Berre.
Yes, thank you, Andre. So I'm happy to be able to present results from the COGNITWIN EU project that we are just finalizing now at the end of 2023, and particular from the Norwegian pilot partners with Hydro and Elkem. So you see the presentations we will have here on the first slide. The project is now at the end of its lifetime. It was 14 partners, and we had 6 different pilot areas. So beside Hydro and Elkem, that we will hear more about, we had Sumitomo on boilers, Sarsdal on steel production, Sidenor on steel pipelines, and Noxel also on steel pipelines. And then we had Sarsdal, I mentioned. Yeah, so that was all of them, I think, supported by various technology partners. It was funded under the area of digital technologies for improved performance in cognitive production plants. With COGNITWIN, we introduced the concept of both hybrid twin and cognitive twin as extension to a digital twin. So it basically reflects the situation in the plant, but with the hybrid twin, we are adding hybrid models, physical models, together with the data-driven models. And with the cognitive twin, we are also adding intelligence and reasoning. So these are extensions from, say, a classical monitoring twin that use this for prediction and prescription. We have also introduced a digital twin pipeline that defines a digital twin from the data that is collected in a sensor context, with data acquisition into a data representation form, and then building up the models, model of the real world, hybrid models with physical models, and cognitive models with AI and reasoning, and also then visualization and control and feedback into the system. For this, we have created a digital twin pipeline reference model that describes all of, say, the technologies that are relevant to have in a digital twin that are following these 4 steps. And we see the digital twin and then the hybrid and cognitive extended twin in the middle here, where we add in more of the physical models and the analytic models. And basically, this is what we have also developed over Toolbox around. So I'll now actually switch into the cognitive web and show what we have there, because now at the end of the project, we do have everything available in our website. So it shall be easy to get access to that. And see the website here. There are various descriptions and examples here. The public reports shows also the documentation, and see there is a lot of public reports on all of the pilots and the technologies. We further have a YouTube channel where you see online recordings of presentations, and we also have the Toolbox portal. So the Toolbox portal is where we have populated the digital twin pipeline with various tools. And in particular, we have 6 digital twin pipeline examples, of which you will see today in more detail: the emission temperature and fan control from the gas treatment center of Hydro Aluminium, and also temperature in tapping stream and slag in refining ladle from Elkem. Then we have also predicting maintenance of machinery, rolling wheel tracking system, hybrid model for ladle refractory wear, and boiler fouling management that are also available, and also have YouTube presentations. So these can be selected, and then you will find a description of the pipelines and of the various tools that are found here. The tools are also described individually. So we have these tools on data acquisition and digital twin representation, use of the assets administration shell standard and data spaces and connectors for that. And then tools on machine learning and on visualization. So in the context of the Hydro and Elkem cases, we will in particular look at now the tools from Cybernetica that can also be found here. But today we have Cybernetica that will present this more in detail as the first introduction. So we will soon go over to that. I will just remind you that this online tool basically contains a directory of all of the pipelines, and I would encourage you also then to look at these others. We might come back to some of these because there are, of course, slightly different focus areas, and then there are different configuration of the digital twin pipelines as we go through here, because depending on the case, it will be different tools and components that are selected and connected from the toolbox that you see here. So it's all available in this context, and there are more detailed descriptions of all of it in deliverables here that describes all of the tools and components individually, as also more extensive information on the pilots and the usage of the tools. There are more presentations on the YouTube channel and also a teacher resource page with all of the publications and reports from an educational point of view that can also be utilized for further education and training. So that was the introduction to the COGNITWIN project. And then I will give the word over to Peter Singstad, who has been responsible for the Cybernetica perspective in the project and also been an important partner in both the Hydro and Elkem cases. So with that, Peter, I will stop sharing my screen and you can take over.
Thank you, Arne. And I'll continue and talk a little bit about first about the products that Cybernetica brought into the project and further developed as part of the project, and then I'll continue showing the pipeline for the Elkem and Hydro cases where these tools were used. So let me first talk a little bit about our main product at Cybernetica, which is Cybernetica CENIT, which is a supervisory control system. That means a system where we, let me see, I'm trouble with my moving forward. Okay. It's a supervisory control system for industrial processes that has the ability to learn from plant data, has the ability to adapt to changing process conditions and optimize the production. And that's what we work about here. And we should do that in a safe way always. And also it should be cost effective, so that we can make a business case out of any new controls that we make, including the ones in COGNITWIN. In the end, it should be cost effective. So we do that for chemical industry. We do it for metallurgical industries, as we will focus on today, including aluminium electrolysis. So this Cybernetica CENIT tool is based on what in science is called nonlinear model predictive control. And it's also based on first principle process models, which means that when we start working on a new case, we start with making a model of mass and energy balances and so on, formulating that model in terms of differential equations. And that's the starting point of developing the control structure that we have in mind. So the mathematical model is key here. Let me find a pointer. And that model goes into a number of sub-projects that is used for developing the applications that we will talk further about today. So on one side, we plug that model into a part of the software which creates what we can call a soft sensor. It's based on an augmented Kalman filter, for those who know the theory here. It has it takes the measurements in. It has the ability to correct the model, to track the real plant, and then make predictions. So that part of the system has the ability to learn from the history. And then on the other side, we have the controller, which is a predictive controller, which means that we make a prediction into the future using the same model. And we, based on that, we make an optimization so that we find the best possible plant input subject to a number of safety requirements or constraints on the plant. So that part has the ability to optimize the future. So this is the core of the Cybernetica CENIT, which then creates a feedback control loop on the plant. So this is part of a bigger suite that we will see more on the pipeline diagrams. Let me just briefly mention the workflow that we are working on here. We typically start with developing the model. Then we have a tool for fitting the model to plant data. So we add plant data, we can fit the model. We can either fit parameters that later on are held constant, or we can also fit parameters that we allow to vary over time, so that we enable this tracking that I mentioned briefly. So that can be set up in the model fit tools. Having made a model, we can just make a simulator. So we have the Proxim tool for creating simulators that is used in a number of applications in the industry. But then we have the online control tool, which is Cybernetica CENIT, where the same model can plug into there. And also, in order to test the controller, we have an online simulator or a simulator that emulates to be an online system, so that we can run the model in a real sim, and we can set up an environment where the CENIT controller actually controls the real sim as a plant replacement model. And that's the final step of testing the system before we really go online. So we turn over that switch and start controlling the real process. Then we have to be at the plant in the end. So that was very briefly about the workflow that we use when we set up this tool. And now I come to one of the pipelines that's on the server that Arne already mentioned, where we have the pipeline for the hydro gas treatment center. So in the hydro case, it was important to collect data from different sources. So here we have a CENIT as part of the online control, or which is a setup to do online control of the gas treatment center. But in order to do that, we had to collect data from different sources. So we have sources from the electrolysis process through Hydro's OPC server. And also we collect less often used type of data. For instance, weather data from the Meteorological Institute, where SINTEF has made a weather API. And we also have data on the raw materials going into an OPC UA server, and we can use that online in the control application. We have two databases in there, Hydro's Trusted Data Lake, and also a database for the Cybernetica tools. And then we have an anomaly detection algorithm that also the online control system can benefit from, rejecting bad data. And we have, of course, interfaces to the users. So secondly, another tool that I would like to mention briefly is what we call Cybernetica Inside, which is a tool for thermal cameras, which is a very new tool that was, so the tool was launched as a tool last year. It has the ability to integrate data from different thermal cameras from different vendors, and we take that into an application host where we collect the data. So this inside service, I'll talk a bit more about that later on. And then we have a web server host and an OPC UA client. The inside service has the ability to have a rather advanced image processing algorithm plugged into it, so that we can take the image data and do tailored algorithms for a particular application, and we will hear more about the Elkem application of that in a few minutes. And then we have, of course, the inside client, which is a type of operator tool. This is just a demo example. It's I think it's a wood burning oven, but most of the pictures we create are sensitive, so that's why. But we have a real-time visualization of images then that the operator can have. They can have multiple images following the situation on different locations or from different perspectives of an oven in the same view. So this tool has been integrated into the pipeline that was created part of the COGNITWIN project for the Elkem case, where we have infrared cameras and the Cybernetica inside frame camera, and then signals go into visualization, and signals also go into the Cybernetica CENIT application also in this case. So okay, that's all from me, and I move on to, I think it was Arne first, wasn't it?
Yeah, now we go to Hydro and Arne. Yeah. Yeah.
Good morning. So I will give you a quick brief introduction to the Hydro part of the COGNITWIN. It was mainly worked on by myself and people from Cybernetica, and as mentioned, the people from SINTEF in this period. The general scope or objective was to define how to digitize the system that we have by using existing measurements, and also develop new and innovative ways to measure and sensors in the system, and then put up models to create the cognitive digital twin that we ended up with. For us, we had to define what we meant with the different things, but we see the digital twin as a basic analytical model, somewhat along the line as Peter mentioned. The hybrid twin is adjusted by feeding data back into the system and constantly adjusting the model. And then the cognitive part is when we take in and adapt the operators' corrective actions and self-corrective actions as the model itself develops. For those who don't know how to produce aluminium, we put together a carbon with aluminium oxide and electrolyze it to aluminium and CO2. And raw gas that we handle in our GTC gas treatment centers are mainly 98% of ambient air, plus the CO2 generated by the process. And in that gas, we also have HF in the magnitude of 200 to 600 milligrams per normal cubic meter, given the process itself. The fluoride balance in the system is key to keep a good yield of the process, because it directly influences the heat balance of the cell, and that's why we want to keep it. Traditionally, electrolysis and GTCs has been operated completely independent of each other, And in this attempt now was to bind them together as a total process altogether. This is the system in question. This is the Karmøy technology pilot, where we have the gas ducts coming from the pots going to the GTC, and the gas is collected from the cells, gone through a reactor where it meets the smelter grade alumina, both primary and also recirculated alumina, to absorb the HF. And mostly these GTCs are working with an efficiency of 99.9 something in terms of recovering the fluoride. And the fluoride is a valuable commodity for us. It costs $1,700 per ton. So we want to recover fluoride as much as possible. In Hydro, we built it up by 4 cases in the beginning, where we have, first of all, meeting the necessary primary alumina feed to the reactor in order to have a flat and a constant fluoride part of the alumina. The second was to keep the reactor temperature under within the best area of absorption of HF. Third one was to regulate the main fans, both to have full control on the gas flow as such, but also to save energy. We also had a fourth case where we wanted to have self-regulating dampers on the cell in order to have constant suction from the cell. However, due to the physical cost of this was dismissed from the project. But it is now continued, also in collaboration with Cybernetica, to bind this together, and we are now running this under our CO2 programs that we are running in Hydro. We had targets for each of them, and that was evenly distributed HF absorbed in the alumina fed to the electrolysis. Keep the temperature within 90 plus minus 5 degrees, and reduce the overall power consumption of the GTC main fans in the system. I will just show this because Peter went through this, but we had a big challenge in our system due to, as some of you know, Hydro was prone to an cyber attack. I think it was back in 2018 or 19, which is why we have been very cautious about how the different communication pipelines across our firewalls has been done. Everything that we do, we will try to protect the process network, but we managed to find a way to do this in a secure way based on the knowledge from Cybernetica and our IT personnel in Hydro. As Peter said, we start out with an equation. This is the model for Hydro case in terms of absorption, is based on a lot of publicized material that can be found within our discipline. And Sudi put this together and put it into the model that is then inside the CENIT GTC of Cybernetica that we used. And what we then found with the model was that we had a monitor that was measuring the HF content of the raw gas. We see that that one every now and then drops out due to obscuration of the lenses that is used on this laser-based system. However, whenever the model comes back on, you can see that it will then represent the same value as measured in the system, even meaning that we can run for a period of times without the actual measurement, which gives us a good trust in the model that was put up for this case. We put up then a dashboard for the operators, which is then in Norwegian here, where we have the inventory of the spent alumina is also prone to certain terms that we want to vary the level of the inventory. We have then, based on this and the predicted HF content of the raw gas, we then put up the feed of primary alumina as a suggestion, where the predicted need in order to meet a certain target is given by the model as such. Here we can see a recording of what was going on in the process in March. Of course, this is put on high speed, so it moves a bit quicker, but we can see that the model aims to, at the same time at least, want to hit the target of absorbed HF. The level of the and the inventory of the secondary silo is constantly adjusted in order to follow the profile desired by the operators. And the set point is then given to the system and following the predicted need for such. In order to keep the temperature, we have internal heat exchanger in the GTC, and we managed to keep, when it was normal production, to keep within the sweet spot as marked on this figure here, both in terms of humidity and temperature during the period which we analyzed. Then we were prone to some curtailment in our process, which then gives us a lot of deviation from the system. But as can be seen here when looking on the data, most of our temperatures were within the desired span of operation. We also developed prior to this, but also further developed within the system, a cheap way to measure high or large duct gas flow by the use of ordinary DP cells with delta pressure cells combined with simulation in CFD, where we get the constants for the system. And then we had the gas flow control in order to control the main fans, but also as a feedback to the model of how much gas with which concentration gave us the amount of fluoride that we needed to meet with secondary aluminum. And when we look on the control of the main fans, we managed to take down as much as 10% of the use by basically putting the gas flow on a constant mass flow in terms of normal cubic meter per hour. If calculating the same thing for the whole collection of main fans that we have in Hydro Norway, this would then add up to 23 to 33 gigawatt hour per year in terms of saved cost, basically by tuning down the fans during the colder part of the day and only gear it up during the hotter period of the day. So all in all, we were able to put through a stable absorption of the fluoride going back to electrolysis. It was based on the model developed by Cybernetica and the cognitive feedback from operators, combined with meteorological data that we got from the APF or SINTEF. We also saw the good effect of having constant temperature in our main reactor of the GTC, and we reduced the power usage as much as up to 10% on the main fans that we had, giving, as I said, 23 to 33 gigawatt hours per year. Plus, a lot of the bits and pieces that we found in this project, we use as spin-off in other cases and continue to work on it in our system. And that was basically it from me.
Yes, thank you,
Thank you.
Arne Dyrøy. So we then go to the last one from Lars Klemet Jakobsson and Erlend Lunnan, excuse me, from Elkem.
Yes. So me and Erlend, we will talk about the Elkem Digital Twin. Title is Elkem Digital Twin Pipeline. We will dive into temperature and slag in the tapping stream and the refining ladle. We also have other contributors, mainly Kjetil Hildal and Kasper Linnestad, but also others have contributed to this work through the COGNITWIN project. So we had a pilot in Bremanger of processing liquid silicon alloys. We had people from Elkem Technology, the internal R&D division, and also the division of silicon products, where all the silicon smelters are. And we had lots of help from the operational personnel at the plant in Bremanger. So the focus is on the treatment and flow of the liquid alloy from the furnace into the refining ladle, and finally casting for solidification. So the main focus was to apply infrared cameras to get new information that we didn't have before starting this project, and also to develop online models for the material and energy balance from the tapped metal to the solidified product. So we had the aim of implementing 3 infrared cameras, one for tapping, one for the refining station, where we also do alloying and fines injection, and finally at the belt casting and solidification there. This presentation is focused on the 2 first. So we have already seen the pipeline where Cybernetica have included or implemented their software and their algorithms. And now for this presentation, we will mainly dive into the algorithms worked on for IR cameras. So I think I give the word to you, Erlend.
Yeah. So when you tap from the furnace into the ladle, the temperature is a very important process parameter because it determines essentially what we can do with the liquid in that ladle. So how we can refine it and how we can alloy it before we cast it. So this temperature budget is critical. So one of the things we wanted to see if we could measure the temperature from the tapping jet using this IR camera. So one of our issues here that you can see is that the temperature over the whole tapping jet is not consistent. So you can't just naively point a camera at the jet and get out a reasonable temperature. And this will, and the tapping jet's shape and size will also change depending on the conditions of the furnace. But what we found was that if we managed to follow a consistent streamline in that jet using our different algorithms, then we get this histogram that we can see here, which follows different points along this blue line, where we can get out a consistent temperature. So here the temperatures are uncalibrated, but you can at least see the consistency. Lars, next slide, please. Yeah, so we also want to know something about the slag that comes from the furnace, because that will interrupt or might disturb the chemical or like the chemical reactions that we want to create inside of the ladle. There is this common metallurgical proverb, which is if you take care of the slag, the metal will take care of itself. So here we're sort of trying to understand how much furnace slag or the unwanted slag that comes from the furnace that goes into the ladle. So here we are using the difference in emissivity between the slag and the alloy to try to isolate out and catch these slag droplets. Yeah, Lars? Yeah, so here we have a camera from the alloying and the refining station. So here we want to know sort of the amount of floating slag that comes into the slag on top. And then we want to try to see if we can measure and follow the liquid alloy temperature. So if like we don't want the floating slag to be too thick, because then if we start to alloy something that cannot penetrate that slag, for instance, then you will just burn it on top, which becomes really expensive very fast. Lars, next slide, please. So here you can see sort of how our algorithm works. So it tries to like isolate the different zones depending on temperature. And Lars, can you go to the next slide? Yeah. So here on top, you can see sort of how the algorithm works. So here we're using a different camera than the one that we had on the tap hole or tapping. So here we say that the colder the slag is, the thicker it is. So we're sort of assuming that you have this heat fall off. And then here you can also see that the thinner the slag is, the warmer it seems to be. This is due to the difference in emissivity between the two phases. So this makes it sometimes difficult to tell the difference between the slag and the alloy, which is one of the issues that we had to deal with. For measuring, and here you can see below there are two different images of slags. So here we have what we call like volume slag indicators. So the lower the number, the less the lower the slag. So so here you can see two differences, and then these fit very well with what we observe. And then we also have to try to estimate the temperature of the liquid alloy. And one of the problems that we saw was that at different points in the alloy, we get different temperatures. So we had to sort of try to find out a way how to deal with this, and this has to do with like dusting and waves. You get these small slag floats that come up and that sort of thing. Lars, next slide. But if we are able to isolate different areas with the temperature, we get these different lines where you can see here that we have this consistency, which allows this inconsistency to be handled while you get quite consistent behaviors over time. Yep.
Yes, so I will finish up this presentation. Here we also see the Cybernetica model together with the temperature from the IR camera at the refining station. And you can see that you have a good correlation between the trend of these two. Here we have scaled the temperature to have a fit between the model and the camera, but the trends are looking very promising. So now I will just summarize. Throughout the process or the project, we started by selecting IR cameras for these different applications, where we concluded that we needed different kinds for different parts of the process. We installed IR cameras to all the parts that we had planned to install them. We had the online model from Cybernetica, including an optimization in that model to have the model hit on to what happened in the real production, and we could see a very good prediction from the model in the end. And then finally, what we talked about now, the algorithms to evaluate temperature and slag in tapping and refining. So that was it. Thank you.
Thank you all for a fantastic presentation. This was, of course, very impressive. And this is also only a part of COGNITWIN project. We are open for questions. I would like to start with just saying to you, Arne, Berre, if you was going into COGNITWIN 2, what would be the next step, you think, from where you ended with the COGNITWIN project?
Yes, so there are, I guess, two parts to it. There is some work that are continuing from it. We heard future plans both from Hydro and Elkem. So it's continuing with further cameras and further cases with the foundation. So that's already in place, but that's of course out of funding of the EU projects. That's internal funding. Further, there are opportunities, of course, for future research and innovations. I think the next step, which we already looked at the end, was, say, the evolution from Industry 4.0 to 5.0 with the operators in the loop. That was part of the cognition we did, to have more interaction using the operator's knowledge and involvement in the process. So already in the final phases, the various pilots and use cases introduced operators in the loop and the use of their knowledge. That's also evident in some of the other 4 pilot cases that we didn't talk about today. So we bring this with us forward in, say, in the Industrial 5.0 with more of the human knowledge involvement and also the evolutions. There are, of course, other things that we are speculating with the new technologies of AI, generative AI, and other aspects that might be interesting to explore also. So there are various ideas that are being thought about in addition to the very concrete evolutions that is coming with the pilot partners.
Excellent. We also have a question from the audience. Slag Grøvland, can you please just come up with your question, please? I think we lost you on.
Oh, you're muted.
Trying several unmuting
here. We hear
no,
you
it's
well.
okay.
Yes.
Thank you. Slag Grøvland from Elkem. I really appreciated that Hydro mentioned the IT security part here. Just wondering, because bringing in especially cloud models or any kind of models to write back to the control system, we have a lot of segmenting in the networks. So I was just wondering if all the pipelines that you have put up, if you have looked into that as well, with the, especially regarding the Purdue model with the 5 layers that we generally have in our systems.
Is that a question for me?
Or the ones who made all the pipelines, if you have looked into the IT security part
I must
as well.
say that I'm so lucky that we have people that take care of this. I also have to follow the rules, so I wouldn't be able to answer you on this specifically. But it took a long time for us to clear out the way we in the end did it, because we didn't dare to open any kind of ports that. So, however, that said, we sometimes felt that once we got things to work, then the cyber security gang came and closed the ports as we opened them. So we had a little tug before we ended up with the solution.
Yes, but I think this is a challenge that we will run into in any company now, when we want to have, like, especially a lot of cloud models are not allowed to write back into the control system. And we are also working on that model in Elkem now, where to put that edge computing as well. So I think also research programs like this should look into that part if you make pipelines.
Thank you. That was a very good point. Any other questions from the authority? Anyone from the audience? No. Okay, then I think we can close this webinar, and thank you all for attending, and especially thanks to all participants from presenting COGNITWIN, and a special thank to Arne Berre. So thank you all.
Thank you. And Merry Christmas and Happy New Year. I guess we don't meet until next in this context.
That's correct. This is the last webinar for the year. Thank you all.
Thank you. See you next year.
Thank you.